Thank you all for making it, especially with this weather. Really appreciate you all coming out. Okay, so with that said, I wanted to introduce, we're going to have 3 talks today, not 4, because of whether one of our speakers couldn't make it. But we'll make sure that the speaker comes, the member speaker, we will have him at a future meeting. In the meantime, we'd like to give a warm welcome to Betty Robinson and Chris Malicki. They're going to speak about the Observer's Handbook. They are both longtime volunteers and assistant editors of the famous Observer's Handbook. Each year, they review the existing materials, they add new materials, and assist with proofreading before publication. With that, let's welcome Betty and Chris.
Thanks, Swapna. So I just wanted to just sort of give a general overview of the Observer's Handbook, since we all get it with our membership. And then when I'm finished talking, then Chris is going to go through and give a bit more detailed breakdown of what information you can find in the handbook. So as Swapna said, Chris and I are assistant editors on the handbook. I've been... My first edition is the year 2000, and Chris's first edition is 2017. And just if you can probably tell the difference in the thickness, and I'll talk about that in a second. So the Observer's Handbook is really important to the society. It's a moneymaker, and being an organization that depends on membership and donations, we need the income from the Observer's Handbook. So it's very special and important. It's been around since 1907. I don't have the first one here with me, but I do have one from 1940. And I'll leave this out, and you can see how small it is and how old looking it is. Oh, and I've actually got one from 1957 as well. In 1966 and 1972. The first edition was 1907. So in the 119 years that the handbook has been available, we've only had 8 editors. So 119 years and only 8 editors. Dr. Chant, who is very important to the society, especially at the beginning of the society, was editor for 50 years. And then other editors had longer editorships, like I think Roy Bishop was 17 years and so on. And one really neat thing about the Observer's Handbook is that it's compiled by volunteers. Everybody is a volunteer. Now, the editor does get an honorarium of $5,000, but I know for a fact that the editor donates that money back to the society. So everybody who works on the Observer's Handbook is a volunteer. And it's world-renowned. The handbook is sold all over the world. It's in most observatories. People look forward to it. We now have our regular Canadian edition, but we also have a US edition too. So that one is mainly just spelling changes, but there are some examples that have been changed to US examples to make it more US friendly. So I mentioned that, it had grown. The Observer's Handbook had grown in size. So if you look at like 2000 compared to 2026, yes, it's quite a bit different. So that happened when Roy Bishop took over. He added, I think he has about 17 sections in here, and they're sections that don't really change much. I think we call them evergreen or something like that. So they can be updated, but for the most part, they don't change, like his information on tides and so on. And actually, in work, when I'm working on astronomy material, then I go to this all the time for the basic data. And if I have to do anything about tides, then this is the first place I go to read because he's an authority on tides. Yeah, we can't make it any larger. We can't do a page count any higher than this, or the mailing charges will change. It'll be too expensive. So this is it. It can't get any bigger than that. And I think that's probably about all I wanted to say before Chris comes up. But I'm going to leave these old editions here if at the break you want to look through them. They're kind of interesting, especially the really old ones. So Chris, I'll hand over to you now.
There's actually 3 people in this room who are involved with the Observer's Handbook, but I'll get to that in a moment. Thank you everyone for coming on such a snowy day. I remember 20 years ago, I gave a talk here about the analemma, and I was with Roy Swanson, was sort of rebutting me, and we were sort of arguing, and it was a very snowy day, and we probably had about 10 people or less, but we still went on with the lecture, and we were asked to give the talk later on again, but he gave his part, but I didn't give mine. I thought once was enough. So again, thank you for coming today. So I put up the US edition and the standard edition, which is not a Canadian edition, it's the standard edition and the US edition, the cover of it. So we're the default edition and the US is secondary to us. We've had a US edition for maybe 10 years or so, and it's not only spelling changes like color and color, O-U-R, O-R, although all those things are very careful that it's in there, but there's also a section that's specific for the US, which will be on my last slide. So I just have to figure out how to change these slides. Let's see. There we go. Okay, so there's about 15 major sections. Right near the beginning of the handbook are these quotes. So again, what Betty had mentioned about Dr. Chant. So the Observer's Handbook was created in 1907. It was second edition in the year 1908. Then there were a few years without it, and then it was published continuously. And the quote below that, each year some 9,000 copies of the handbook are distributed to many countries throughout the world, to amateur and professional astronomers, to educators at schools and universities, at the many observatories, planetaria, and library. Not planetariums, planetaria. Like, how correct is that? The handbook is the main source of income for the RASC, and et cetera, et cetera. Okay, and then the next quote. So Roy Bishop, who has one of who has the most sections in the handbook and was a previous editor. The Observer's Handbook is the single most useful publication for the observational astronomer. Its combination of authoritative data, informative diagrams, and concise text is unique. Anyone interested in astronomy, beginner or expert, amateur or professional, student or teacher, will find the Observer's Handbook indispensable. Its international reputation for quality is a credit both to its many contributors and to Canadian astronomy. Now, you can go on Google and find all this stuff in the handbook, but to have such a huge amount of information in a non-virtual, like a printed thing like this, it's all there, like, really, I think that's sort of unique, probably unique in the world. Anyways, near the beginning, there's a whole section on, I'll give you examples of the 350 pages or so. So here's the bottom of one of the pages near the beginning, symbols, signs of the zodiac alphabet. I mean, if you look at sky charts, stars, the brightest stars are Alpha, Canis Majoris, Beta, Orionis, Gamma. So here you've got the Greek alphabet. So you can easily just refer to there and know, okay, it's Zeta. So that's, probably the 6th brightest star. Like the zodiac constellations and their signs, and there's official symbols that the planets and the moon and the sun have. They're in there, of course. I was hoping Raghav would be here, and I know he is. In one of the quizzes that you gave us, the question is, how big is how many degrees is this or that? Well, there it is. Like, it's in that Observer's Handbook right there and there. There you go. There's a very detailed scientific and data-filled section called astronomical and physical data. Here's one page on the left. Like, we're not going to go over this in detail, but look, in the middle of the page on the left, you can see all the major wavelengths that you use for filters for nebulae. Like if you're doing imaging, like what wavelength you want, it's right there. Like you don't have to go on Google or anything. There it is. Angular relations below that. On the right side, light grasp, limiting visual magnitude. What are they? Like very useful equations. Like looking near the top, the focal ratio is equal to the focal length divided by the diameter. I mean, we should know that when we're using telescopes, but if you forget, you don't have to go on your phone. You can open up page 33 and find it. Okay, here's the third contributor from our club to the Observer's Handbook. Randy Atwick has a 2-page section on voyages in the solar system. Very interesting. Like, there's a lot more voyages than can be shown on 2 pages, but I think he's very nicely summarized all the really critical, important ones. Every year this is updated. I mean, it'd be nice if we had 10 pages for this, but like, no, look, 1967, Apollo 1. I mean, you're not going to take that out. That's important. Vostok 1, 1961, first human in Earth orbit. Like if you want to know when that happened, just go to that page. Now I've got an enlargement of the last page right here. So the bottom part is updated every year. What I really like, and I don't know where else you could find this information, look at that part near the bottom. As of July 2025, a total of 709 people have traveled into space. You really need to be a super space, enthusiast to know that. Like, where are you going to find that information otherwise? Like, only somebody who really is interested in this would put that in. Like, all these sections in the handbook are written by people who are really expert in their field, professional, amateur, but very meticulously done. Like, just a wealth of information again. Okay. There's a very large area called the MOM, month by month. So I showed, here's January. Like every month has 2 pages. So on the left side, for the first time this year, on the left at the very top, you've got the planets. And before it used to give their declination and right ascension, now it gives the constellation that they're in. So that's one change that has happened this year. So Jupiter is at near opposition. So of course it's in Gemini right now. If you look at Jupiter, how far away is it in astronomical units, its magnitude, how bright it is, size, and then a big description on the left of each of the planets, the sun and the moon, and what they do. Now on the right side, a day-by-day description of what's going on. I took the right side and made an enlargement of it. So it is Friday the 16th, so near the bottom, but in universal time, it is now about 0 hours, Saturday 17th. So if you look at that lower, I don't have a pointer, but look at Saturday the 17th. You can see the phase of the moon. It's almost new. On the extreme right, you've got Jupiter and where its satellites are any moment. So you go out right now with your telescope. You look at the number 18 line, and that's where you'll see the Galilean moons. Sure, you could look this up, but it's all in this book here if you want.
Libration.
The libration dot. Yeah, that's a part of the moon. Yeah, there's a huge amount of detail there. Yeah, that part of the moon is tilted towards the Earth the most. Yeah, thanks for pointing that out. Okay. Now, Betty talked about When she wants to talk about tides, look up tides, she goes to this section. This is one of my favorite sections in the book. It doesn't change from year to year. I think it is extremely scholarly. Roy Bishop lives in Nova Scotia near Halifax, I believe. So he's very close to the Bay of Fundy, which has, with the Ungava Bay, it has the largest tides in the world. So he's a super expert on tides. You read this, there's just so much information in here. There's a nice picture of how what tides are. I am going to go on to so the lower part of the right page, right there. Like, how many of us know this? 5 basic astronomical periods significantly impact the tide. So in order, there's 12 things that influence the tides. They're listed in order of their length. So the shortest one is the semi-diurnal thing. So every 12 hours, there's a certain influence on this tide. Every 12 hours and 25 minutes, there's influence because that's when that thing is below the moon. Like the moon moves. So the amount that the moon moves. So if you have the moon in one place, you're halfway away from the moon 12 hours and 25 minutes later, because the moon has also moved out of your way. And then going on, I won't read all of these, but each of these has some influence on the tide. I found a very interesting, number 11, perigean or spring tides are a tide where it's full moon or new moon. So every 4.43 years, you get a recurrence of that. Okay, and the Fundy tides, like I love the Bay of Fundy. I've been there many times. The tides are enormous. And here, Roy describes very well why the tides are so large. So going to the second paragraph, the primary cause of the immense tides of Fundy is the resonance of the Bay of Fundy Gulf of Maine system. The system is effectively bounded at its outer end by the edge of the continental shelf, with approximately 40-to-1 increase in depth. The system has a natural period of resonance of 13 hours and is driven near resonance not directly by the moon. So not directly by the moon, but by the dominant semi-diurnal tides of the Atlantic Ocean. Like, I didn't know that until I read that. Like a father pushing his daughter on a swing, the gentle Atlantic tidal pulse pushes the waters of the Bay of Fundy, Gulf of Maine, up nearly to optimum frequency to cause a large oscillation. So you're not going to find this information in many other places. Okay, so now we get to other sections where we're up to page 182. Now, I could have picked any of these pages to show you. I like this one because it's got a really nice diagram of sunspots, the penumbral, the light bridges there, and a good description of that. Very nicely done. And further about the sun, this section changes every year as we get 1 year later. So at the bottom, you see a nice diagram of the sunspot cycle with the 11-year phases. So if you look at 2020, number 24 in the year 2015, when that observer's handbook came out in 2015, they were writing, well, it looks like the sun is losing its activity, and maybe the sunspot cycle will end, and we're going to get another Maunder minimum like we did in the 1600s, where there's very little solar activity. And people were wondering, what is cycle 25 going to be like? Like many of the theoreticians were saying it's going to be even lower than 24, and there'll be hardly any solar activity. Well, we certainly know that's not the case. Like, look at all the auroras we saw last year, and look how high cycle 25 is going. So I like getting the handbook every year and just looking how that graph is 1 year later and what's happening. So it looks like we're actually over the peak of this current sunspot cycle, and we're starting to gently come down now. Well, we'll see what happens in the next observer's handbook. Can't wait to see. Okay, There's a very large moon section. Like I picked these 3 pages because they're talking about the lunar eclipse that is coming up in less than 2 months. So, the late Fred Espenac did this section, beautifully written, lots of detail, got pretty well everything you want, like a map in the middle where the eclipse will be seen. You could see North America is going to be seeing the eclipse as the moon is setting. So as the moon sets, the sun is rising. So that's late into the night before dawn. That's when we'll see a total eclipse on March 3rd. On the right are the predicted times when the shadow of the moon covers and uncovers given craters. So Sky and Telescope magazine for many, many years has been collecting observations of people who are timing when does the shadow get exactly to the midpoint of a crater. These are the predicted times, but the actual time could be off by a few minutes from the predicted time. So if you want to do that, you'll know, well, at 10:08 Universal Time, which is 6:10, no, it'll be date, no, it's still standard time, 5:10. This crater Timocharis the shadow should be halfway through. Well, you could observe and see, is that the case? Is it off by a few minutes? And that way we know, is the Earth's shadow looking larger or smaller than predicted because of clouds in the atmosphere or murk, or maybe a volcano went off and made the shadow bigger. So things like that are interesting things that amateur astronomers can do. Okay, I know Murray Paulson from Calgary, I believe. I met him on an eclipse expedition. He's a real, he just loves observing planets. He writes this great section every year about the planets. It's about 20 pages long, or even more than that, 25 pages long. I like that diagram at the bottom because it shows the biggest and smallest size that each planet can look compared to each other. So Venus at its largest, when it's a crescent, looks larger than Jupiter does at its biggest. What surprised me is look at the difference in Jupiter. I mean, to me, Jupiter sort of looks the same all the time, but look, when it's at its farthest point, it's looks much smaller than when it's at its biggest. 29.8 seconds versus 50 seconds. Here's his section on Mercury. Part of his section on Mercury, he's describing what Mercury is, what happens during the year. At the bottom, there's a really nice diagram showing how bright Mercury, the diameter of Mercury, how large it is. You can see where we are January that Mercury is at western elongation, so it's a morning object and it's about to go behind the sun. And just before February starts, it's in superior conjunction behind the sun. You can tell that from that diagram. Okay, so moving along. I picked this. Jupiter has a large section. There's several pages on the occultations of the satellites of Jupiter. There's just so much I can show. So I decided to do this. I like the diagrams in the handbook. Like here's a nice drawing. If you look at Jupiter, what are you going to look for? There's belts, zones. Zones are light colored, belts are dark colored. This is the correct, well, this is the north up. The way, if you see it through a refracting telescope, it would be the opposite, or through one mirror, be the other way around. Anyways, it's got all the features. On the right side, you've got the 4 Galilean moons, how large they look, how bright they are. Just a wealth of information. I like this one. Here you've got the section on Saturn. You can see January, February, and then you've got the other months below that, and then the next page you've got June. So in any case, see how the rings are tilted. They're getting more and more opened up as you get later into the year. So what is Saturn right now? Well, it's the 17th, right? No, it's the 16th, but universal time, we're on the 17th. So go to number 17 at the bottom. You can see that if you're looking at Saturn through a telescope, Titan is going to be on the extreme left, and the second brightest moon, Rhea, is on the right. Okay, again, I don't have a pointer, but you could see that if you follow that line for January 17th, because we're at that point right now. Okay. And there's a nice asteroid section. Every year, there's a different asteroid featured. Last year it was Vesta. This year it's Iris. So Iris is in Leo. So this will be a nice thing to follow in the spring, where it is, a detailed chart, where it is. So next year we'll have another asteroid. And these are the brightest minor planets or asteroids for 2026. I was wondering, why are they in the order that they are? Well, it's by the date of their longest elongation. Sorry, I have to look that up again, but there's some there's some rhyme and reason to it. In any case, the asteroids where they are on given dates. And in the last 20 years or so, the handbook has had planetary occultation section. Like stars can be an asteroid or a body other than the moon can cover a star for a brief period of time. Here's the tracks on the Earth. Like David Dunham is probably the world expert in this, and his section has greatly expanded. In the last few years, there's many pages on occultations of asteroids, of other objects, of moons, of planets. And he's got special sections where spacecraft are going to go to a certain body, and that body we want to study. So when is it going to occult stars? So just reams of information about that. Okay. Now, okay, so we're moving right along. Okay, so the stars section. Okay, what did I want to say about this? Okay, the brightest stars. Everybody likes Betelgeuse, right? These are, I picked the chart that is for winter. So from 3 hours 55 to 6:23. So this is winter. So see Betelgeuse near the bottom, 6 from the bottom, Alpha Orionis. So that's its name, Alpha Orionis, Alpha from the Greek alphabet, like I showed you before. Right ascension and declination, where it is in the sky, it's a magnitude 1.9. It's variable. If you remember, in the year 2019, Betelgeuse dimmed, so it's a variable star. Next, Alpha. Okay, where are we? Oh, hold on, I'm looking at the wrong thing. No, 0.4. Sorry, I'm looking at the 0.48 variable question mark. Okay, and then we've got its color, B minus V color. It's the type of stars. It's an M star, which is one of the redder stars. And then pi, milli-arc seconds, what its proper motion is in thousandths of an arc second per year. Okay, on and on. So a wealth of detail of all of these brighter stars. Nearest stars, that's another section. The sun is the nearest, and of course we all know Alpha Centauri and Proxima Centauri as being the second closest star system. But what's next? The next one after that is famous Barnard star, the star that has the fastest proper motion in the sky. It's the number 3 system. And look at Sirius, the really bright close star to it. There's still 2 brown dwarfs in front of it. And number 6, Lalande, 21185, that star is closer than Sirius. And look at its magnitude, MV, right near the right, it's 7.46. So it's visible with binoculars. So that star in Ursa Major, you could see it with binoculars and certainly with a small telescope, and you can find that sixth closest star system to the Earth. A lot of detail here. What is its spectrum? A rad at the top. How quickly is it going away? Like how many kilometers per second is it rushing away from us or towards us? So if it's going away from us, it's hold on, I should do this. Anybody help me out? Minus is towards, right? Plus is away from us. Okay. Oh, number 15, 61 Cygni, one of my favorite double stars. A and B, very close to us. Two components, almost exactly the same magnitude. Okay, and then, okay, here's a question for everybody. There is an error in this chart. Yeah.
Found it.
Oh, yeah. What is it?
No.
I will.
It's printed too small.
No. Okay. I've been a proofreader for many years, and we never managed to do an issue without errors. I just happened to put this table up on this, like in my presentation, because I thought it was interesting. I'll show you a double star thing, and I look at something and said, God, that's wrong. I look at my references. Yeah, in fact, it's a mistake. And I sent James Edgar an email a few days ago. On page 291, there's an error in such and such. And he thanked me for picking that up because nobody else had picked it up. I will buy a calendar. The first person who can tell me where the error is.
On the street. In the handbook, on page 291.
Yeah. Well, while we're trying to find it, we can go through, show you what some of the, how much information is some of these things. So let's pick a star here. Then a double star. Okay, let's go to the fifth one from the bottom. Alpha Canis Majoris AB. That's Procyon. So you've got where it is, right ascension and declination. That's longitude and latitude. The magnitude is 0.4, so you know it's very bright. The brightest of the stars is 0.4. The next one is 10.8. So you know that they're very different in magnitude. And position angle. What is this angle from north going around? How many degrees? How far apart they are in seconds of arc. At the end, you've got the period, 41 years to do a complete rotation. Okay, anybody found the error before I go to the next slide? Okay. No, that's correct.
That's correct, because I was looking at the average magnitude.
Well, the thing that's Procyon, the bright star in Canis Minor. So it's a first magnitude star, and it has a white dwarf companion. So the white dwarf is very faint, so it doesn't add much to the total magnitude. Like I was looking at that, I looked at a star and I said, no, that can't be right. It can't be beta. It's got to be a lambda. And in fact, that was the case. Okay, look at the 1, 2, 3, 4. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, look at the 10th thing, Beta Orionis ABC. At 5 hours 14. That's Betelgeuse, right? Oh, no, that's Rigel, Beta Orionis. Okay, right ascension 14.5, Beta Orionis ABC. Yeah, that's Rigel. So go down a bit more, about halfway, and you find another Beta Orionis AB at 5 hours 35.1. See that one? Yeah, that can't be beta. There's only one beta in Orionis. That's in the head of Orion. So that should be lambda Orionis.
I got it.
Yeah.
I'm throwing out my hand.
So that's what proofreaders are supposed to do. And I consider it a failure that I didn't pick this one up. We should pick it up before it goes to the publisher, not after, not that you have a website and you say errata, these are the errors, da, da, da. That's what's going to show up now. Anyways, there's a nice sections of observing. There's probably the one that's been around the longest is the Messier object. So I'm not going to show that because we all know the Messier objects. But look at this nice table from near to far. Like the closest one in this is the Pleiades, and the farthest is the brightest quasar. So as you go down the list, you get progressively farther and farther objects. What is their designation? What is it? OC, open cluster, RN, reflection nebula. At the second from the bottom, G, galaxy. Then sizes, how far away they are. They're progressively farther and farther away in their common names on the right. So there's a nice list for you to try to observe. There's the Messier catalog. There's also of 110 objects. There's also the new general catalog finest objects, 110 objects. None of them are Messier objects, but they're all probably about as good as the famous Messier catalog. So I showed the winter ones that are observable right now. Hubble's variable nebula. Okay, well, there we go with those. Remarks. We can take one of them. Which one do I like? Oh, the one at the very top, Perseus, Cyanchi Perseus, one of my favorite. Naked eye with binoculars, you see two clusters, a double cluster, double asterisk, really beautiful. Use low power so you can get both clusters in at the same time. Wonderful object to see. Okay. Here's the dark nebula. I think this is a dark nebula. I can't see it. Yeah, because the green thing is over the title. Yeah, but these are dark nebulae. So you're looking for something that is a nothingness. Like I really like these objects. You see stars and nebulosity, and suddenly there's a whole area that's blank. There's nothing. That's a dark nebula, and some of them are so obvious. As I mentioned in one of my talks before, for years, people wondered, are dark nebulas just holes in the sky where there's nothing? Or is there something in the way that we can't see what's behind it? Well, Barnard, all these B objects for Barnard, who did a photographic atlas of the Milky Way over a century ago, a lot of these objects are named after him. He came to the conclusion that a dark nebula is not a hole in the sky. It's actually dark matter like dust and gas that's obscuring what's behind it. So the stars are still there. They're just being masked by something in front of them. So that's a dark nebula. Okay, and see, there's a number of tables there of things to observe that you don't usually see anywhere else. Like, look at these. I think these are the wide. I can't see the top. Yes. So these are all objects. As it says at the top, in recent year, wide field eyepieces, refractors, fast reflectors have increased in popularity. Transparent skies have become attractive observing destinations. So these are objects that are very large. Like you can see them with the naked eye or with binoculars, but you need a nice dark sky to really see them well. Looking near the middle, NGC 1499, the California Nebula, very large, but you need a nice dark sky to see it. I've seen it with binoculars from the Okanagan Valley in BC. Okay, finally, this is my last slide. So this is a page that's in the US edition that is not in the standard edition. In the standard edition, we have a fairly large section on light pollution and light pollution reduction. That section is quite a bit shorter in the US edition, and instead they have a specific thing for them. So this time they're talking about the Astronomical League, and I think it's turned 80 years old, and that's about that. Okay, so that's the end of my presentation.
All righty. So this potato here is pretty important, and we've discovered a lot of neat things about it. But just looking at the picture, you can get a pretty good idea that it's not really a solid object. It's just a big pile of rubber, and that rotational energy makes it squash and gives it that ridge around the middle, so it looks like a potato. Anyways, I'm going to translate this. This is an article written in Nature Geoscience called the mineralogical, there's a word I haven't pronounced in years, evidence for hydrothermal alteration of Bennu samples. Sounds entertaining. If I get too technical, cut me off. A long time ago in a galaxy far, far away, I got a degree in geology. So occasionally I might get carried away with that. So here we go. So why is this thing important? This is all the article. We'll skip that. And what they did with this article is they ran it through X-ray diffraction, X-ray fluorescence, scanning electron microscopes, mass spectrometers, all these great toys to figure out what's this stuff made out of. Well, it's first of all, Bennu is a carbonaceous chondrite. And no, that's not something you need medication for. And what it is, Bennu, a carbonaceous chondrite, means it's a carbon rich, and it's a chondrite, means it's loose rubble. So we need the samples from this are important because the only carbonaceous chondrites that have landed on Earth as meteorites, there's only been 6 of them. And all 6 of them have suffered thermal alteration and exposure to Earth's elements. So this is pristine sample that we got from this thing. Very important. So we see. And what did we find out? Well, this is seriously cool. It's a rubble pile. We knew that just by looking at it. It's rich in carbon. It's got water in it. It's got a lot of water in it. So with the neat thing, there's water everywhere in the solar system. And you think, look at a big black blob that looks like a potato. It's got a lot of water in it. And it's made up of hydrated silicates. Big sophisticated term for on Earth, a hydrated silicate would be something like a clay. Very similar. And sulfide minerals. It's also important. Sulfide, not sulfate. Sulfide minerals are usually just a metal with sulfur attached to it. So like a mineral called forsterite is iron, nickel, and sulfur in a sense. So they're evident on there too. What else we got? Well, we found out, and we'll explain to it why, but it's a rubble pile that originated from a larger asteroid, a larger object. Could have been a planet even, or a planetoid in the formation of the solar system. How do we know that is? We'll get to that. The primary mineral in it is a mineral called serpentine. You don't care. It's just basically olivine. If you ever looked at a green rock, igneous rock when you're up north, well, you add water to olivine and another mineral called pyroxene, which is the little black flecks you see in granite. You add water to it, you get serpentine. And there's evidence of geological term, aqueous alteration. It's been altered by water, and likely happened when the water was part of the material of the parent plant. So we know it must be something bigger, because do you think liquid water could exist on Bennu right now? No, it'd be frozen. It's too cold. But we do know that since there's all these hydrated minerals, at one time there was liquid water flowing through the rocks that make up Bennu. And there's also the sulfide material, and they come from precipitating out of that aqueous solution, that water solution, in brine and dissolved metals and sulfur in it. And the interesting thing is, the minerals that precipitated out, we can tell by those minerals that the minimum temperature that those minerals could have formed, those sulfide minerals could have formed, was at -25. That's the lowest temperature. Very likely was higher. So we know that there was liquid water in the parent body. And the other forms, you get the usual sulfides, magnetite, you get some carbonates. You even get something very similar to the limestone. It's a rock called dolomite. You can see dolomite on Earth when you go to Niagara Escarpment. The top rock, the hard rock that makes the one, that's dolomite. And what it is just limestone with lots of magnesium in it. And there's phosphates and evaporites. Evaporites are minerals like, for instance, your wallboard is made up of gypsum. Gypsum is an evaporite. It's made from seas filled with lots of minerals in it, evaporate, and you get the stuff that's left over. So here's a picture of that. So the one in the top, this one here, is that little thing there is 100 micromillimeters, so that's 1 millimeter. So it's a very small picture. And this big gray matrix is that serpentine or the hydrated silicate rock holding it together. This neat thing is this thing here is one of those sulfide minerals that's probably forsterite, iron, nickel, and sulfur as a crystal, but most of the stuff is smaller. This little thing is a carbonate on it, and if you look closely, you can't see from that, but it's got all sorts of little pits on it, and all of these things have little pits. This little diagram shows you sulfur on the top and nickel and iron, and it shows you it's mostly iron sulfide is what the predominant one. Geologists love charts too. Now, when you look at space weathering, the surface of Bennu is constantly bombarded by micrometeorites and by radiation, cosmic rays, and solar radiation. And the individual grains of the sample return show pitting from micrometeorites, as expected. You would do that. And the crystalline minerals, so like the sulfides in the previous picture, they show signs of alteration where cosmic rays have flown through the crystal and left a trail of ionization or of altered mineralogy through where the cosmic ray went through. But the surface, if you look at the time fine of what you would expect on the surface, you would expect a heavily pitted surface because Bennu's been around for a long time. But if you look at the surface weathering and the cosmic ray exposure to the minerals in the return, it's only 50,000 years. So those things have been sitting on the surface of Bennu for 50,000 years. But Bennu is much older. So what can we conclude with that? The material of Bennu, because it's a rubble pile, from heating and cooling and orbital stress as it goes around and affected by other objects as it orbits the sun and goes near, churns. So it's a constantly churning rubble pile. It's kind of interesting. And that at one time it was part of a larger object and it was subject to enough heat through either accretion when things compress down, even rubble piles, you compress down, the heat builds up because you're taking heat from this area and putting it into a smaller area. And the other neat thing about it is all the elements of life are on there. There's amino acids in the sample. That's pretty interesting. There is all the organic molecules. So carbon, oxygen, nitrogen, chlorine, phosphorus, they're all in there. And so could the building blocks of life for Earth come from one of these crashing into the Earth before we had a big, thick atmosphere? So I think this thing is pretty, the discoveries in this are super important. The other thing, interesting thing, is it's very similar to the samples returned from Ryugu by the Japanese mission that brought it back. And they're very similar material. So these things are pretty common out there. And, if you got stuff that's got water, amino acids, and the organic building blocks and the elements needed for organic chemistry, I think the universe is pretty much wired to provide life when a suitable environment happens. So this thing's important.
All right, as we're setting up, I'm just going to introduce Raghav, and he's our last speaker for tonight. He's going to speak on Northern Lights and his 5-inch tabletop daub. So welcome, Raghav.
Okay, hello everyone. Since we have already had some really useful knowledge thanks to our previous speakers, let's get ready for a quiz. No, I'm just kidding. Just kidding. Yep, just making sure it's compatible. Okay. Can everyone see it, or should we turn off the lights? Because it's too dark. In October 2025, I was traveling overseas to attend a family event. And since I knew I would be flying over Atlantic Ocean, I thought, since I already knew I would be traveling over Atlantic Ocean, I strategically planned to get my seats, make sure they're on the left side. Because I was hoping somehow I may get lucky enough to be able to see Aurora. Even if I don't get to see it, there was no harm. It would still be a bottle one sky. So here is a bottle one sky. Can anyone guess or identify the constellation featured in this image? So you were all right. It is indeed Ursa Major, as many people call it. Or like I prefer to say it, a rat who was running so fast and ended up stopping suddenly. Now try unseeing that when you see Ursa Major next time. Okay, so I was minding my own business, enjoying the bottom one sky through the window. And suddenly, I see a green, faded halo on the horizon. And guess what? I pull out my camera. It was indeed Aurora. So in the beginning, it was just a small Aurora on the horizon. So even though it was not much, but I was still pretty excited because I went in with expectation of seeing nothing. Yet still, I got to see Aurora on the horizon. And as it was starting, you could say the arc was expanding of the Aurora, if you consider it from the North Pole. It was splitting into two, almost like a hamburger on the horizon. I'm not sure if you're able to see it, but I hope so. So as you can see, there are two waves overlapping. And as these images were actually captured only a few minutes apart. So, and I was not using any editing, no long exposure. These are just random images from my phone. As you can see, the details kept getting more clear and clear because the waves, or you could say the swirls of the aurora, were so dynamic. And then it started to fade away. I thought, oh, okay, it was it lasted for a short duration. That's fine. Nothing to feel disappointed. But guess what? It went back. And oh, this is not the actual aurora. So as it was fading away, I thought, how about if I just push up my ISO on my phone just to catch last few more glimpses of the aurora just fading away. So this was a test shot. Don't worry, it's not actual aurora. So you can see how grainy it is. So I tried to optimize a bit more to be able to capture some more. But while I was trying to optimize or calibrate it, I noticed the green is still not going away because the aurora was actually intensifying again. This was a second phase. So it's still getting brighter. You can see the swirls. Now I'm not even using night mode in it. This is how bright it was in just a day mode camera. And this is just another image because while I was admiring the aurora, I thought, why not take an image of the space itself when there's nothing to worry about the clouds? So that's still Ursa Major, but from a bottle one sky, just above the Atlantic Ocean. And you can still see at the bottom, there's still some aurora peeking in. So that's an image we not often get to capture. And as you can see, after it peaks for a few images, it again started to fade away. I was like, whoa, it has already surprised me once. I wonder if it will do it again. And guess what? It did. And this time it brought its friends. This time it was not only just green, it had red on top too. So you can see it almost has a structure of a wave, just like an ocean wave coming to a beach. I won't, because this is such a short presentation. So if you want to stay me on a picture, feel free to let me just stop by. No worries. And this is how bright it was. It was actually, I was able to see the green, red, lightish green color on my hand if I put it on the window. And now you must be wondering where I was exactly when I captured this image. So I quickly open up the map. This is where I was. I was close to Iceland at that time. And it was almost around 9:30 EST on October 24th. Because dinner had not been served yet. They were still waiting for it, but the lights were still off. So I got lucky, I guess, again. This was just a stroke of luck. And not only I get to see Aurora 3 times, but the cabin lights were off too. And this was the last time when I saw it away. And unfortunately, it didn't came back. So this was just a see off after this one. And this, I would say, it's more of a happy accident. So I was trying to take my phone has a feature to take long exposures for, let's say, it can take a long exposure for 6 seconds. So while I was trying to do that, my elbow slipped from the armrest and my phone somehow decided to, if you want Aurora, why not have it on the whole screen? So this is just Aurora exposure on the whole screen. And of course, when I went back home or whenever I had access to the computer, I went to NOAA's website to extract the images of the Aurora from that day. So these are the images captured by NOAA 21 in VIIRS day-night band from October 24, 2025. And these are the images from SNPP. There's another satellite which follows the same polar orbit, captured at the same time. Now you must be wondering, why is this mosaic in this wavy shapes? And the reason for that is, this is how these polar satellites actually take images of the Earth. They basically rotate on the, you could say, the same space. It's the Earth which is rotating through their axis. So that's how these images are captured and then just assembled into a mosaic. And that's it for our story. Excellent. Let's move on to the next one. So once I arrived at my family's home or my homeland, you could say, all the experiences which I learned ever since I joined RASC, I wanted to share that same experience with my family as well, because they, just like me, they were always also curious about the night sky. They also wanted to explore the night sky with a telescope. In fact, for some reason, telescopes are still considered among general public who are not into, you could say, haven't been introduced to astronomical clubs yet. They still think telescopes are only for scientists, or you can only find a genuine telescope in an observatory. You won't be able to see it otherwise. So I wanted to introduce them to the very first steps to the astronomy or the astronomy club experience. So I decided I would buy a telescope for them, but I wanted to be as convenient as possible for them, because I do not want it to be a chore. Just like, no one wants to carry an 8-inch top around because it's hardly fits in even a standard car. So I chose a tabletop top. Here are some quick specifications regarding that scope, which I chose. It has a focal length of 650 millimeter humble. It's humble focal length, but still good enough for planetary. Aperture was 5 inches. I was looking for to get as much light as possible. Weight is surprisingly only 14 pounds, which is nothing. You can carry the scope in one hand and walk around. And height of the scope was only around 2 feet, so not too high. Just like most scopes, it had a 1.25-inch focuser. Great for solar observations with a compatible filter. And the reason why I chose this image because I wanted to show you how small or big it actually is when it's next to a, let's say, adult person. Because in images, you may not get an idea how big a standard tabletop top could be. And here are some drawbacks. I'll go to benefits too, but here are some drawbacks. Because these entry-level scopes are designed to be for amateurs only, most experienced users usually go for astrophotography or giant truss tube Dobs. The build quality of this scope I did not found to be really convincing. It seems almost the manufacturer was trying to keep it as affordable as possible. And it seemed in their workmanship too, but it was still operational and functional. So no complaints about that. And as the name suggests, it's a tabletop Dob. You will indeed need a table because it doesn't really have any mount to bring it up to your eye level. So as you can see, this image is on the floor. You cannot observe like that. You will have to lie down on the floor. And not the best scope for astrophotography too, because it's a tabletop Dob, which is designed to be for entry-level amateurs who are still trying to learn or taking their first steps to learn the night sky. And DSO observations from the city sky would be challenging, but possible if you're dedicated enough. And here are some benefits. Just like I mentioned, your observing sessions do not have to be a workout. A tabletop Dob will change your mind regarding how simple it could be to just get out and observe the night sky whenever you want. You don't have to worry about, even if it's a small patch of clear sky, if you have a tabletop daub, you can go out, observe, come back in within minutes. It's basically like a giant monocular for you. Children friendly, learning curve is too small. They don't need to really worry about any typical technology, or they don't have to go to user manual. Within few weeks, they can start learning the night sky on their own. And no need to worry about a shroud anymore, because often we use in conventional daubs when people chase apertures, optical tube assemblies do get heavy. So they try to adopt the truss tube design and they have to worry about a shroud thing. But then they have to worry about the DU aspect as well. Every time they have to assemble their scope when they go to observation site. So with this tiny scope, you are good to go out of the box. And as I said earlier, it removes any possible hurdles for you, which will prevent you to go out and observe the night sky, which in my humble opinion is the best feature of a tabletop daub, because often when, let's say it's a clear sky, what's the first thought which comes to your mind? Oh, I will have to go out, I will have to pull out my heavy scope. It's too much trouble. I can't be bothered. I'll just stay inside. But with this scope, all of that problems are solved. Now, since I've shared so many features, so here are some images which I captured with this very scope. So here's an image from sun from November 6th, and you can see the giant sunspots. Those sunspots were actually visible even with the unaided eye. So I tried to look through the sun with a filter, and those sunspots were visible. Here's moon through the same scope. And since I mentioned the focal length of this scope is around 650, so let's say even when you try using a 9mm eyepiece, your maximum magnification would still be limited to 72. Theoretically, you can push more with the Barlow lens, but I don't think so it will have any benefit. So 72 is good enough magnification for beginners. Can anyone guess the object? Which object is this? Yep, Orion Nebula. So DS, as I said, this image was actually captured on a full moon night. So DSO observation is also possible. And would anyone like to guess this object? It's Jupiter. My phone is not really doing justice to that image because we know how phone cameras work. But through the scope, through the eyepiece, I was easily able to see the bands nice and sharp. And that is it.